Hello learners! Today's lesson focuses on implicit differentiation, a crucial calculus technique for finding derivatives of implicitly defined functions. We'll explore its applications and master the necessary steps through clear examples and practices.
I'm Lorenzo Miguel Gallardo, and today I will be tackling implicit differentiation. Implicit differentiation is a technique in calculus to find the derivative of a function that is not implicitly defined in the form of y equals f times x. Instead, the function is defined implicitly through an equation relating x and y. So let's get started. Okay, now we're going to differentiate both sides with respect to x. So first step is d over dx times x squared plus y squared. So equals d over dx times 25. This gives us 2x plus 2y times dy over dx equals 0. Okay, now the next step is we're going to solve for dy over dx. So over here you can see that it's 2y times dy over dx. So now equals 2x dy over dx is equals to negative xy. So this result tells us the slope of the tangent line to the circle at any point times x and y on the circle. Take note that the derivative is expressed in terms of both x and y. Let's move up to another example. Now for the next step is we're going to solve for dy over dx. So we have here is x squared times dy over dx plus 2xy times by dy over dx is equals to negative 2xy minus y squared times x squared plus 2xy times by dy over dx is equals to negative 2xy minus y squared dy over dx. As you can see, it's equals to negative 2xy minus y squared over x squared plus 2xy. And now if you get it, I hope. Now we can proceed to the next example again, and it's going to be more complicated than this. So I hope you learned something for this part of the example of involving products. Now let's move to the next part. Okay, now for the second example it's about involving products. So we're going to find dy over dx for the equation of x squared y plus xy squared equals 6. First step is we're going to differentiate both sides with respect to x. So here we'll need the product rule of d times uv over dx equals u times dv over dx. Okay. Now as you can see, we plus v times du over dx. And now we're gonna move to so after that, for both terms on the left side is d over dx is times by x squared y plus d over dx. D and over dx is times by xy squared equals d over dx times again by 6. Okay, and now the next step is 2xy plus x squared times dy over dx. So this becomes the 2xy plus x squared times dy over dx, and plus the y squared plus 2xy times dy over dx, and now it's equals to 0. So, and the next step is okay. Now for example number 3, a more challenging example. So now next is we're going to find dy over dx if sin times xy equals x plus y. First is we're going to differentiate both sides with respect to x, because this uses the chain rule and product rule of d over dx plus sin times xy equals d over dx. Okay. And now next is for times d plus y cosine times xy times d over dx times xy is equals to 1 plus dy over dx cosine and times xy times y plus x times dy over dx is equals to 1 plus dx over dy. And now for the next step is we're going to solve for dy over dx. So y and cosine times xy plus x cosine times xy is times by dy over dx is equals to 1 plus dy over dx cosine and times by xy to negative 1, and d times by dy and over dx is equals to 1 and 1 is equals to 1 and minus y cosine times xy to times xy is dy over dx is equals to 1 minus y cosine is times by xy over x cosine x times by xy minus 1. And so these examples demonstrate the application of implicit differentiation in various scenarios. Remember the key steps: differentiate both sides, apply the chain rule where necessary, and solve for dy over dx. The resulting derivative will often be an expression involving both x and y. And this will be the end of our session. So I hope you learned something, and thank you for the time for watching this. Goodbye.
Hello everyone, I'm Gab Saona. So in this video, I will be telling you about logarithmic function at kung saan galing ang logarithmic function. What is a logarithmic function? Logarithm is simply a special way of writing an exponent. So here we have an example of logarithmic and exponent function. Yung pinaka sa taas, it is a exponent function. It is b base to x equals y. So kapag kinonvert natin siya as logarithmic function, it will be log y base b equals x. So ganun lang naman siyang kadali. So here, we have another example. We have 2 cube equals 8 x. Sorry. So yan. At we will turn it into a logarithm. So we will having a log 8 base to 2 equals 3. Ganun lang siya kadali. Napakasimple lang. So, paano nga ba natin ma-identify kung ang given ay isang logarithm? So, ito lang naman yung example nun. We have fx or pwedeng any kind of letters. Kasi hindi lang naman fx yung applicable sa logarithm. Now, let's solve for another example para mas malinawan kayo. Let y equals fx. So, we will be finding fx if 3 base to y minus 1 is equals to x. So, ayan, isosolve natin yan. First of all, we need to do is to turn this given into a logarithmic function. So, we will be having here a y minus 1 equals log x base 3. Quite simple, right? Pero hindi pa dyan tapos. So, since yung value lang naman ng y yung kailangan natin, dapat mag-isa lang yung y dyan. Tatanggalin natin dyan yung negative or minus 1. Ililipat lang natin siya sa right side. So, since nilipat natin, dito sa baba, mag-iiba yung sign niya. And now, we will be having y equals log x base 3 plus 1. So, to finalize and to also simplify, we will be having an fx, kasi pinalitan lang natin yung y ng fx, ayun, fx equals log x base 3 plus 1. So, ayun, that's all. That's all about logarithm and logarithmic function.
Hello everyone, my name is Christopher Masal. I'm from grade 11 STEM 1A and I will be discuss arithmetic function. What is arithmetic function? It's like a tool of exploring number. An arithmetic function take a positive whole number like 1, 2, 3, so on and so forth. As input and give you back a complex number as output, which could be regular number or involve imaginary parts. Now, there's 3 ideas of arithmetic function. Number 1, expressing properties. These functions are designed to tell us interesting things about numbers. For example, the divisor function. Sigma sub k of n tells you how many divisors a number has. For example, the number 12 has 6 divisors like 1, 2, 3, 4, 6, and 12. So, sigma sub 0, 12 equal 6. Number 2, irregularity. The value of arithmetic function can jump around a lot. This makes them interesting to study. Number 3, series and function. Some of these functions has neat formulas that involve infinite sums called series and function. These expansions are useful for using the function behaviors. Now, let's proceed to the types of arithmetic function. We can categorize the arithmetic function based on how they behave when dealing with multiplication. Number 1, completely additive functions. These are like others. They satisfy the rule a of m equal a of m plus a of n for all natural numbers m and n. Example, the prime omega function. Omega of n counts the number of prime factors in a number, including repetition. Omega of 12 equal 3 because 12 equal 2 times 2 times 3. Number 2, completely multiplicative function. These are like multipliers. They follow the rule a of m n equal a of m times a of n for all natural numbers m and n. They also have 1 equal 1. For example, the Liouville function. Lambda of n is 1 if n has an even number of prime factors, and negative 1 if n has odd number of prime factors. Number 3, additive functions. These work like others, but only for co-prime numbers. For example, the Euler-Toscan's function. P of n counts the number of positive integers less than or equal to n that are reliably all prime numbers share no common divisor other than 1. For example, the discrete prime omega functions counts the number of different prime factors of a number. Like omega of 12 equal 2 because 12 has two different prime factors na 2 and 3. Number 4, multiplicative functions. This works like multipliers, but only for co-prime numbers. They also have a of 1 equal 1. Example, the Euler-Totient functions P of n counts the number of positive integers less than or equal to n that are relatively prime to n. And now, here's all of example of arithmetic functions. Divisor function. Sigma sub k of n. This function adds up the kth power of all the divisor of n. For example, sigma sub 1 of 12 equal 1 plus 2 plus 3 plus 4 plus 6 plus 12 equal 28. Sigma sub 0 of n is special case counting the number divisor of n. Number 2, Euler-Totient function. P of n, this function counts how many numbers less than n relatively prime to n. For example, P of n 12 equal 4 because 1, 5, 7, and 11 are relatively prime to 12. Mobius functions. Mu of n, this function is either 1 or negative 1 or 0, and it tells us about whether a number is square free. Number 4, Ramanujan functions. Tau of n, this function has more complex definition involving infinite product, and it's closely tied to modular forms. Powerful tools in number theory. And now, let's proceed to applications. Arithmetic functions are everywhere in number theory. Prime numbers, functions like phi of x, help us understand how many prime numbers they are of to a center numbers. Number 3, modular form and elliptic curves. The Ramanujan tau function is connected to modular forms, which are important for studying elliptic curves and other fascinating objects in a number theory. Number 3, contrography. Arithmetic functions are used to encryption because they are fast to compute. Even for very large numbers. And now, this is the end of my presentation. I hope you understand. Thank you.